Hello, in this podcast we're going to use graphical analysis to derive four very useful kinematic equations that we can use to analyze both constant velocity and uniform accelerated motion. Let's get started. First, we would like to come up with an equation for calculating velocity at any given time. We have our graph here. It's a velocity time graph, and this graph tells us the velocity at any given time. So if we can come up with an equation for this velocity line, we will have our first kinematic equation. Now with this line, we can go ahead and calculate the slope a while. It's negative 9.8 meters per second squared, and we can find the y-intercept, which is 0 meters per second. Now let's move on and develop the equation for this line. We know, using our template, the dependent variable velocity is going to be equal to the slope, negative 9.8 meters per second squared, times the independent variable, which is elapsed time, plus the y-intercept. So these are specific numbers for our data that we plotted in figure 1, but we want to make this a general equation that we can use all the time. We know that the slope equals the acceleration, and the y-intercept is the starting velocity at time equals 0. We can make these substitutions to come up with the general velocity equation. So where there's negative 9.8 meters per second squared, I'm going to replace that with the acceleration, and the initial starting velocity of 0 meters per second squared, I'm going to replace with the symbol v sub I. And this gives us our first kinematic equation. The final velocity is equal to the acceleration times the elapsed time plus the initial velocity. Let's move on to our next equation. We'd like to find an equation to calculate displacement. Here we have our velocity time graph again, the same one we used in the previous slide, and we know that displacement is equal to the area between the time axis and the velocity line. So here we've got a time interval from 0.2 of a second to 0.5 of a second, and at 0.2 of a second the velocity is negative 2 meters per second, and at 0.5 of a second the velocity is negative 5 meters per second. However, I want to create a general equation, so I'm not going to use these specific velocities and times. Instead, I'm going to use t sub I for the initial time, v sub I for the initial velocity, and I'm going to use t sub f for the final time and v sub f for the final velocity. This shape is a trapezoid, and our equation for the area of a trapezoid is 1/2 h sub a. H sub a is this height, plus h sub b, that's this height, times b minus a. b minus a gives us the base, because this is point A and this is point B. Now I'm going to go ahead and substitute in. I know that h sub a is equal to v sub I. I know h sub b is equal to the final velocity. I know that point A is equal to t sub I, the initial time, and point B is equal to the final time. So that leaves us with the displacement is equal to 1/2 v sub I plus v sub f times t sub f minus t sub I, and I'm just going to label that equation B. We know from our first kinematic equation on the previous slide, we know that the final velocity is equal to the acceleration times delta t plus the initial velocity, and we know that delta t is equal to t sub f minus t sub I. So I'm going to substitute these into equation B. So where I have v sub f, I'm going to put this expression, a times delta t plus v sub I, and I'm going to put delta t in here in place of t sub f minus t sub I. And when I do that, I get delta x is equal to 1/2 v sub I plus the acceleration times delta t plus v sub I, that whole quantity times delta t. So what I'm going to do now is I'm going to take the delta t and I'm going to multiply it by every term in this parentheses. And when I finish rearranging this, I wind up with the displacement is equal to 1/2 the acceleration times the elapsed time squared plus the initial velocity times the elapsed time. And this is our kinematic equation number 2. So now I have two equations, one for velocity and one for calculating displacement, but they both require us to know the elapsed time. So now we'd like to come up with an equation without time. And for this, we're going to start with equation B from the previous slide. Delta x 1/2 times v sub I plus v sub f times t sub f minus t sub I. Remember, v sub I is the initial velocity, this is the final velocity, this is the final time, this is the initial time. Now I also know that the acceleration is equal to the change in velocity divided by the change in time. I'm going to take this expression and rearrange it so that I have t sub f minus t sub I is equal to v sub f minus v sub I divided by acceleration. So all I did was take this equation and rearrange it. And the reason I did that is that I want to take this and substitute it up into equation B in place of this expression in parentheses. And when we do that, we get delta x is equal to 1/2 the initial velocity plus the final velocity in parentheses v sub f minus v sub I divided by the acceleration. Next, I want to rearrange some terms. I want to take this acceleration and put it over here with the 2. And so when I do that, get delta x is equal to v sub f plus v sub I times v sub f minus v sub I divided by 2 times the acceleration. Then I want to multiply these terms in the denominator. So these are the two factors of a polynomial. And when I do this multiplication, I wind up with v sub f squared minus v sub I squared. So that's the final velocity squared minus the initial velocity squared divided by 2a. Now I'm going to do one more rearrangement to solve this for the final velocity squared. And so when we rearrange that, we're left with the final velocity squared is equal to 2 times the acceleration times the displacement plus the initial velocity squared. And this gives us kinematic equation number 3. This is a very important equation. We don't use it often, but it's the one we can use when we don't know the time. It is the only one of the 4 that we can use when we don't know the elapsed time. Word of caution with this equation, make sure you realize that it's velocity squared. So when you're done solving for this, you don't have the final velocity, you have the final velocity squared. So you need to take the square root of this in order to find the final velocity. Let's move on to our fourth and final kinematic equation, and we'd like to come up with an equation without acceleration. So far, the first 3 equations all require us to know the acceleration. Here, we have figure 1 again. It's the same velocity time graph we've been working with. We know that the displacement is equal to the area of the trapezoid. So here in this light purple or pink, we have the trapezoid area, and we know that that's equal to the displacement from t sub I to t sub f. And in this case, we know our initial velocity, v sub I, and our final velocity, v sub f. Well, I'm going to draw a line halfway between v sub I and v sub f. Now, if we just use the graph to look at v sub I is negative 2 meters per second, v sub f is negative 5 meters per second. So halfway between 2 and 5 is going to be 3.5. So I'm going to draw a velocity line at negative 3.5 meters per second. Why is this important? Well, this negative 3.5 meters per second is the average velocity during this time interval. I'm going to go ahead and draw a rectangle area using the average velocity line. And let's look at the area of this rectangle compared to the area of the trapezoid. Well, if we look right here, the trapezoid has some extra area. This is an extra area that is not in the rectangle. But if we go over here, this triangle is some extra area that the rectangle has that the trapezoid doesn't have. And notice that these 2 triangles are exactly the same area. So that means that the area of the trapezoid and the area of the rectangle are exactly the same. So that tells me
that the displacement can be represented by this trapezoid, or the displacement can also be represented by the rectangle created with the average velocity line and the time axis. That leads us to this equation. This expression in the parentheses, v sub I plus v sub f divided by 2, that is just the calculation to get the average velocity. And we multiply it by delta t. So this gives us our fourth and final kinematic equation. The displacement is equal to the average velocity, which we calculate by adding the initial and final velocity together and dividing it by 2. And once we have that quantity, we multiply it by the elapsed time.
Well, this ends our podcast. I hope you found this helpful, and have a good day.